Hi, I'm Rohan Bull, and this is my Lab 3 magnetic field of a bar magnet analysis. So, the overview of this lab is to relate magnetic dipole moment and magnetic field. This is an extension of the Biot-Savart law, which is modeled up below. We also have a purpose in correlating magnetic field with distance and being able to code these magnetic field models in GlowScript. So in the actual experiment, we first had to locate the magnetometer sensor on our phones. To do this, we first put a magnet at the end of a east-west meter stick and kept our phone perpendicular to it. We moved our phone up and down till the X value was at its max and the Y value was at its min, and then we marked it with tape. And then we rotated our phone horizontally and repeated this process, except looking for a maximum Y value and a minimum X value. Mark it with tape, and the intersection of the tape is the sensor. And then using this sensor, we find the distance from the magnet to the sensor that produces a magnetic field of 20 μ-teslas. And then we record that distance and repeat the test 2 more times. We repeat this step for magnetic fields of 70, 120, 170, and 220. So some of the variables and assumptions in our modified Biot-Savart law is that, well, first B is a magnetic field, and then the variables inside the equation, mu is a magnetic dipole moment, r is the observation vector, and some assumptions about this is that everything is constant except for r, which simplifies the equation down to the magnetic dipole moment of the bar equaling to kr raised to n, where n is assumed to be a constant of -3. So here's some of my measurements, all averaged out due to the spreadsheet and the resulting graph due to them. So the graph produces the equation y equals -3.0275x minus 14.411, and correlating that with the equation up above, ln k is the constant here, so it equals -14.411. And doing a little rearranging, we can have it so that the absolute value of mu is equal to k over mu naught times 4 pi over 2. And as I stated before, the expected slope is -3, and our calculated slope is -3.0275. So the error is actually around 1%. So that was the on-axis magnetic field. Now this is the off-axis magnetic field. This is to measure the magnetic field a distance d perp in both the x and y directions, where my average d perp was 0.173 and my average net magnetic field is 0.000179 teslas. All of the recorded data is listed in the chart below. So here's some of the coding, just coding the constants, creating a magnet at the origin, which is just a cylinder, creating the magnitude of the moment, which is multiplied by the values that we calculated in our graphs. And B scale is 2000 for the arrows, distance, how far away from the origin in meters, and then just vectors for perpendicular lines and observation locations. So here's a little bit more coding. For the off-axis calculations, the d perp 0.173, the actual distance d, the observation 45-degree angle. And here's what the output of all that looks like. As you can see, there are the observation locations, the magnet in the center, and the corresponding magnetic fields. So reflection questions. What if we hadn't oriented our experiment to compensate for the magnetic north? Well, every value would have been skewed towards the magnetic north. So that's why we had to account for it. What if we were to stick two identical magnets together and run the experiment again? Well, this would just double the power of the magnet. We would assume it's one instead of two, and all the directions would be the same, however, the strength would double.